guess yeah, we are nearly 20 people. So very short intro on myself. This is Ugur Yavas from Eatron Technologies. I am head of AI at Eatron. And today's topic is all about thinking what happened in the AI nearly in the last 10 years and what their influence on battery space when it comes to software development and also deployment from e-bus fleets to two-wheelers or energy storage systems. I'll try to go through and let me start. So there is almost like three acts I see, and I'll try to start from the very outer layer, which is about what is going on in the world. Just I mentioned there is a huge hype around AI, and lately it's all about, let's say, language models. But beyond that, I think there is very interesting points that influence how we can work with the battery data when it comes to battery analytics or state estimation. So that will be captured in the battery world. And I think there are key trends happening. Just before in the keynote, we hear about data center race. What should be the true chemistry for that? Is it lithium ion, sodium ion, or the flow batteries? So many different angles, little time to develop. So I'll try to project what is going on the world for the batteries. And finally, the harness part is sort of the essence of the talk. Whatever the models or the intelligence is being developed, the harness surrounding of it or the system built on it will define the product, will define the success and value proposition. So let's go one by one. Then for the world side, and what is scaling? So one of the brightest minds in the AI world is Andrea Karpathy, ex-Tesla, ex-Stanford nowadays. He's working for Anthropic. He coined this software 102030 terms. And what it is 10, we could say, the classical software, line by line, human writes it. Most likely we try to come up with, let's say, equations, approximations that is, let's say, calculatable, sometimes provable. And that is the world maybe until 2010-ish. Then with software 2.0, what Karpathy terms is now what you are learning is weights through a nonlinear optimization from a large scale data. And software 2.0 really scaled and, let's say, got very popular, especially in the self-driving industry, when you need to collect maybe billions of kilometers and you need to validate your vision systems or decision makings under vast amount of, let's say, scenarios. And again, ImageNet challenge, I will keep telling the ImageNet 2012, a very important breakthrough. All of a sudden, a deep neural network came to the very top at the image classification task with a deep learning. So that was like the start of software 2.0. And with the recent stream of events with the ChatGPT and Claude and maybe all the other Geminis around it, what we are now hearing more and more is harnesses, tools, skills. So a lot is happening. Even what is called prompt engineering is transition to context engineering. And that blends kind of the software 3.0. And anything we are doing today, there will be blend of these three layers. So another thing about when I was saying ImageNet, and let's stick with the 2.0 analogy for a while, because the second section of the talk will focus on software 2.0, so the neural networks. What is changing with neural networks that leads all the way towards today's GPTs are actually ability to learn from very large, diverse data with a scalable model. Another very bright mind, Andrew Ng, shows this slide maybe 10 years ago, but still is the truth. If you have a machine learning, let's put linear regression or any kind of curve fitting algorithm, your performance will not scale with the data. At some point, you will simply bound, you will simply converge. But what we are seeing is the real difference When you insert more data, if you can increase your performance, that is the essence of scalability. And that is what we are pursuing, actually. And when these kinds of scalability talk, we think there is the famous article by another, let's say, AI thought leader, Rich Sutton. Eventually, the large-scale data and compute will beat hand-engineered cleverness, but that is not like a very bad news because, again, what I say just before, the engineering will keep appearing on the harness, on the how you design the network, the loss function, the training curriculum, and how you really evaluate this for the robustness and deployment. So there is a lot going on after the model. Model is just a small piece. Then let's look at a very promising example from the self, let's say, driving space. British startup from called Wave. What they are doing is, again, they call it AV20 by the same analogy by Karpati because they are advocating end-to-end. And let's look at this chart because we'll see how this will translate to AI later on. And what Wave claims here, when they train their driving network completely on a UK benchmark and bring to the US, the zero shot means the model has never seen any source of data in US and directly evaluated. So this is kind of the gap with their ideal UK performance. And the next question, what happens if they feed hundreds of hours of US driving? There is a 5x improvement. And another stream, what happens if they 5 times increase the US driving? Now it performs 40 times better than the initial zero shot. So by just to put again zero shot, meaning I learned from, let's say, dataset A, I arrive to dataset B, in this case US. I know how to drive. Maybe I learned generic driving skills, but I never drive in US. But I still able to drive. And when I observe to some data from there, things will get better. That brings us to our sort of AI vision at Eatron. We want to create foundation models for batteries that will able to estimate state of charge, voltage, state of health, and their future propagations, remaining useful life, and anomalies. While doing so, we want to be grounded on the physics because many of these things may touch on the safety critical spaces. And moreover, without having this physical ground and domain knowledge, these problems are not even tractable or not will be scalable between different chemistries and different applications. Finally, the third round, we want to put this is obviously not a must. We can run everything in cloud, but what we are seeing is embedded intelligence really matters. Everything we talk about in the next slides, besides the LLMs, can run on the very, let's say, traditional MCUs like PSOC6 or RxTC3. You'll see some you can see some ASOC numbers from runtime in milliseconds, some RAM, ROM, just to give you an idea. So let's transition to the battery space now. Maybe a lot of outside talk, but just to warm up. What do we see in battery space? So in Eatron, we are very good at modeling, let's say, the cells in a traditional way to come up with equivalent circuit models, then combine them with state estimators like extended Kalman filters or Lemberger observers. And I think most of the large internal teams in the industry, they follow a similar structure, and things will get very tricky for the LFP because of the flat OCV, but eventually, let's say every conventional lab, we want to characterize the cell, we want to get this model. And the problem here, this takes too much time. And the second problem, it is not compounding. You almost start from zero when there is a new cell, even within the same chemistry, because AH is different, maybe OCV will be different, DC, IR, direct current internal resistance will be different. So these resets basically explodes the time you spend in the lab, so delays the process. Then, if we move, let's look at the industry. So here there is one quote from our recent engagements with a very high-level director from an automotive company, and there is like an obvious trade-off. Rather than extracting the absolute maximum from every single cell, every single program, they want to achieve the trade-off with minimal engineering effort, regardless of whose cell we use. Because program after program, there are different suppliers, or there are even different technologies, as we just heard in the previous data center topic again. Sodium ion is getting more popular. LFP was new maybe 3 years ago. Now it's an old story, and the industry is moving. And another striking screenshot from a McKinsey, let's say, analysis. This is old school OEMs versus new, let's say, disruptor OEMs for China, how many months or years it takes for a new model launch. And in 2 years, there's like a new car there. And it was used to be 4 to 5. And this is the same in the Europe. And if you have this much time, maybe you have all the luxury to characterize your cells, do your lab testing, you will be getting along. But the reality shows most of the time you don't, so you need something compounding. And that brings us to the Eatron. One of the things we need to emphasize, because I think in order to succeed and in order to get the best out of software 2.0 approach, so the neural network approach, it starts with the data, obviously. And when it comes to data, there is like a big, let's say, diversity. It starts with the testing the cells in the lab cyclers, maybe putting packs on the labs again with the very clean environment, regulated temperature, minimum amount of noise. Then when we came to the field, maybe it starts with a small pack, which is like a two-wheeler, then like a larger pack for a passenger car, then strings of packs for a big e-bus, and things might get stationary, and things could be in a UPS where it just sits and waits, dominated by, let's say, calendar aging. And a battery could be in a second life, actually. And the first life, it was doing any of these things here. So there's like a huge diversity. Every, let's say, vertical here may bring its own noise factors, usage conditions, environmental specs. So at Eatron, luckily, thanks to our engagements in the last 5 years, we have data from every single thing here. And you can see some numbers. So the big numbers, basically, very short story. We have large and diverse data, but that alone is nothing. So when I say at the beginning again, data is just one pillar. We want to have a large data, diverse data, lab and field combined. But then the second, or maybe most important thing, you need an algorithm that will learn from there. Then you can achieve what Wayve achieved self-driving cars. And here we are trying to think we'll have multi-chemistry, diverse temperature conditions, diverse usage conditions from fast charge to standard CCs to the grid storage profiles, while you have irregular pulses that will create a backbone that will make a huge pre-training. And then that model, as I gave the example in learning from UK, driving in US, from day one, it will be able to perform. And if it collects more data with this new environment, it will get better. So that is like our pitch, our approach. And in the next pages, I want to show this is actually working. Starting with the maybe pre-trained, and also here we can anchor a bit about model-based or state-of-the-art approach, because again, just recalling at Eatron, we are not blindly developing anything with AI. We have a very strong model-based team where we model the cells with equivalent circuit models, then design extended Kalman filters. And that brings an opportunity to us because as a, let's say, AI engineer, I can always go and check how I perform with respect to this, let's say, conventional, very accurate approach, but taking, let's say, time from the perspective, and it has its weaknesses from some different angles. And this was with our customer, a very comprehensive multi-temperature with a controlled lab environment, but a lot of noise injection to prove these software are working. And you can see head-to-head numbers. And what we are seeing is AI is, although using, let's say, less amount of particular domain data, because of its large pre-trained corpus, it still performs as good as the model-based. So this is like the starting point. The average errors are near. For the max cases, it is sometimes worse, but these are single points. So there are, let's say, filtering methods, smoothing methods to make them better. So they are as equally good or very, very close between AI and model-based. Let's look at from the different angles now. One thing very important, and I think when I say about engineering the right model, what you do in training is very critical. And here what we are seeing is one of the very important case, you may lose your starting point. So in this diagram, what we are seeing is the reference SOC is actually 90%. This is a LFP cell, as you can guess from the voltage. So now you are in the flat zone. So it's very difficult to initialize, and you give your models. Actually, we have AI SOC, and also just to show clone counting, you start from 10%. Then what happens next? Clone count obviously does not do anything, maybe because of some current offset or anything accumulated. It gets slightly better to 80-ish%. But what AI does in this orange, even if it's in the flat zone, it slightly corrects. Obviously, it's not making a big reset, but even in the flat zone where you don't get much from the voltage, it corrects. And eventually, if you leave the flat zone where you have now more sensible information from the voltage, it quickly resets the error. This means almost acts like a Kalman filter. So what we are doing is we are able to teach these things during the training, and when we test outside of the training in a case never seen, the model reacts plausible. Then a very interesting case. So I already said zero shots in the self-driving example. What would be our zero shot in the battery space for AI SoC? Introducing a cell which is not part of our pre-training. And that was the case with a proof of concept with one of the Japanese OEMs. What we are seeing here is from day one, they provide us the data and we'll share our estimation. And you can see even in the -10, model performs 1.5% average. This is LFP again, one of the widely used LFP cells in the world. So what we are seeing is the model is from day one, in average less than 2%. And when you tweak the model, introduce different kinds of errors, it is still resilient. So it's not fading away. It's not, let's say, destroying itself in terms of performance. So very promising zero-shot results. Then the second thing we should think, again, from the same analogy, I'm performing at some level at zero shots. But what does it mean for my improvement points? Can I improve if I observe more data? Now I switch to a different program. And in this case, again, what you are seeing between red and green is reds are our pre-trained performance. And at the end, it is the zero shot or pre-trained. They will not perform perfect under all conditions. This is not our claim. Our claim is they are drastically reducing the data you need. And with this particular customer, what we observe is, I'm just showing you the -10 to 0 degrees, because when the things are warmer, all these numbers were again nearly 2%. So in average, with all the noise factors we have, we were performing less than 3% in average, which is a good starting point. But in the cold, it was not that good. Then what we did, we fine-tuned, and you can get this drastic improvements when we now show the model, okay, this is a new cell you've never seen, and you are not good at the cold temperature. Now this is your opportunity to learn and improve yourself in the cold temperature. Then another thing, I think when it comes to state of charge estimation, I can summarize maybe three big challenges. One is performing at the cold, I already showed. Another one was recovering from a wrong starting point, especially in the LFP. I show a few pages ago. And another big question when it comes to how serious we are talking is end of life. And what we are seeing is this cell's SOH, state of health, is nearly 80%. So maybe end of life for some programs or near to end of life. So 80% SOH. The profile you see here now is from a best profile. If I'm not mistaken, it should be either solar or peak shaving. And the essence is, so far, whatever I show you, all these results are from a single model. So that's very important. Now we switch to an end of life, to stationary storage. And what we are seeing is model is still performant with the average error of 0.89. And you can see the distribution. I was saying again, maybe I can zoom in a bit. Sorry, it's not zooming very well. But the essence is occasional 3% errors, then the distribution gives you an idea, nearly maybe 2 sigmas around 2%, 1.5%-ish, and yeah, very good average performance. And what you can see is the current profiles here, the SOC trace here, and the model itself, it also guesses the voltage. And this connects us back to one of the points about it has to be some kind of physics in the model. It doesn't have to be equations. It could be loss function. We like to use loss functions, or we like to teach model more than just a number. SOC perhaps is just a scale factor, but if you know about the voltage, you'll know more about electrochemistry. Let's get going. So now transitioning to the lifetime prediction. So what we are seeing here in the next pages, we'll look at some data. Let me explain how this plot will be read. In the bottom x-axis is equivalent full cycle. So if you are not doing 0% to 100%, you're doing a partial cycle, we'll count those and normalize to the equivalent full cycle with respect to your nominal capacity. Here we are seeing the SOH. This black line will be the historical SOH. This dotted gray lines will be the prediction starting points. The blue line will be the future reference SOH. Then the amber dash is what AI model thinks about history. And orange dash is what AI model thinks about the future. So here, with the same approaches I show in the state of charge, now we are talking about lifetime estimation and prediction. So our AI model will build its own historical SOH, then it will start rolling it out for the future. Then let's look at some real-world field data, how things are going. And one of the important angles about degradation, there are two major phenomena. One is calendar aging and the other one is cyclic aging. And what we are doing is we are just designing a single neural network, again, with the right portion of the training data, with the right loss functions. The single model will figure it out whenever the calendar aging is dominant or the cycling. And here, this LFP case, calendar aging is dominant. We are seeing equivalent full cycles up to, let's say, 450 or 500, nearly 5 years. So it is very, very shallow cycles, occasional use. So we expect to be calendar aging to be dominant. And now what you are seeing here is explained. The historical SOH is constructed by the yellow trace. The future is blue, and our guess is like the orange one, and we make a maximum 1.5% SOH error. And this is when we know about 20%. So by just having 100 EFCs, we can roll out a prediction up to 4 times more. And in the second example, if we just start to know about 50%, and now you see that the historical SOH tends to be converging what is the actual, and that also helps a bit on our prediction. So the max error from 1.49, it dropped to the 1.1 for the state of health. And you can see the average numbers here. I'll get going. I'm also checking the time. And another example, I already talked about aging mechanisms, and we need to know the knee points because degradation is not linear. At some point, it will accelerate. It will actually start rapid, slow down, and go rapid again. Here, what we are seeing is a EBUS application, and our model is, again, making predictions. And this time, as you can see, it is way off. And I think that is the essence of remaining useful life. You cannot predict the future because the future usage will change. When it comes to a bus, it gets into maintenance and do nothing for 6 months, or it could have some periodic duties which correlates with the school time. So maybe in the summertime, the bus is not working and the model thinks it already learned that. So it gives this break and it makes degradation. But what happens in reality, for this particular bus, the shift changes here. So then there's like this drastic usage, which accelerates faster. Obviously, model is not able to predict that. But very important angle, if you know that usage will change, our AI model can act as a simulator. And by saying that, you can fit different future usage conditions. What happens if I increase the charging rate? What happens if I now move to an environment? Maybe I was used to drive my vehicle in Alaska, but now I move to Phoenix. The temperature will change dramatically. What will happen? So what you're seeing here is the black line was the original prediction. And when we apply higher C-rate charge, it dropped like this. And when we apply higher temperature, it dropped like this. And based on this little historical SOH, maybe just after 30, 40 cycle. So for this particular case, what we know, if you observe this part, it will get better, the prediction. Or if you fit this future, it will drop, let's say, a lot better than this error. And finally, to conclude RUL and just providing different, let's say, applications from two-wheelers to e-buses, from BESS, from different chemistries. Once again, the exact same model. By just having few assets here, you can fine-tune and get the results I am showing in this page. So the very last section, we talk about the AI trends in the world, how they look like for the batteries when it comes to the software 2.0, so the designing neural networks. That's almost like an old story now, because these days it is all about agentic loops, agents, cloud code, cloudbot, codex, GPTs, and that is quite new. But what is not changing, in my opinion, this is a famous paper from Google. The year is 2015, and the name is Hidden Technical Debt in Machine Learning Systems. And as a data scientist or AI engineer, everybody loves to come up with a new machine learning model, the solution, the neural network, perhaps a new network type, new architecture. But it is the tiny piece. In 2015, Google was so aware of this, and they were saying, in order to deploy these things at scale, you need a lot of surrounding things. And when I see this picture, it reminds me this. Today, what is going on with cloud code, which is like the state of art of anything you can use for the coding tasks or reasoning tasks where you can really go something deep. The LLM is just sits here, but it's surrounded by engineered artifacts, requires domain expertise, requires software expertise, requires product expertise, and these are just some examples. So the core LLM might change from Sonnet, Opus, Kimi, many open source models or the closed source famous ones. Whatever it changes, the success is also with these layers. How you orchestrate them, how you design few agents cooperating with each other, how you handle reasoning, chain of thought, how do you maintain the memory, the context, how do you inject everything you know about the documents, and what tools these agents can use by having exposed to which skills. These will change the things. And I think this is not different from what we see here. Very, very similar. And yeah, although 10 years or 15 years in between, still we have the same thing resonating. And what it means for what we are doing, I show we have very strong neural networks designed to estimate state of charge, RUL. But in addition to that, what we are trying to craft is very similar to the previous pictures. Now we call it BOSS agent for BAS. This is our agentic AI loop that sits on top of existing software, and it has access to the very specific things for the application and customer. That could be battery specification, maintenance log, service manuals, agent skills for that. And in conjunction with that, two main agents, one will do for root cause and other will do for the maintenance. And to explain this in an easier way, let me go through quickly a video stream because I want to leave time for your questions. What we are seeing here now, this is from one of our real deployments from last year, and there was like an imbalance issue, and our existing software stack was already pointing out here. But here, what you see here, how an agentic loop can make a difference, because dashboards are endless, dashboards can get busy. Eventually, you may feel having a agent explaining everything to you at ease. And in this case, perform a root cause analysis on current events. And current event was imbalance. So after some time, obviously things are not in the speed of light. I'm just, rolling forward. What we see here, the agent checks, it says there's like an isolating cell balance issue. These two cells are critical. This is the data it's backing up. And then you can understand further, what is this? And obviously, we are talking about predictive maintenance, or we want to plan an action on this. And the follow-up is, okay, I have this imbalance. It shouldn't be there, actually. The BMS should take care of the imbalance, but whatever happened, I monitor this via cloud and I see this. And now, can you plan the action for it? And what it comes up with is very interesting. This is a real-world issue we found. The text could be small apologies for that, but it says it will not balance by itself. The software-based balancing is not feasible because here what it does in background, it reads the specs of this BMS, this system, and it finds out the two cells are below from the rest of the pack. And when two cells are below, the BMS will not discharge rest of 300 cells to just balance two cells. That is the fact about this system. And now there is only one choice, making a maintenance intervention. And the agent already bringing all of these to the operator. And just to conclude, what we are doing at Eatron is our main product is battery optimization software. There is physics-based and neural network-based software pieces for performance, lifetime, and safety. We are flexible for running on BMSs, EMSs, or in cloud, or all together. And we have the agentic loops working in tandem with all these software. And Eatron is very shortly. Thank you very much for listening us. For anybody who doesn't know Eatron, we founded in 2018, nearly 45 people. We have key partners and customers from investors, customers from industry, just to name few. We can speak publicly. And I talk a lot about results, networks. We have also many patents about these technologies I just showed. Thank you very much.